Alright, hello and welcome to another physics problem tutorial. So today we will be looking through number 16 in chapter 11 of this textbook, which talks about angular motion. So this problem here is all about conservation of kinetic energy in introducing rotational kinetic energy. So if we look at this problem, we see that we have a non-uniform cylindrical object, which means that I is no longer half mr squared. So we see that it starts at the top of this slope, rolls down without slipping, and then flies off this edge and goes a distance d. So first off, we want to set up an equation for conservation of kinetic energy because we have no non-conservative forces that do work on it. So we can say that we have initial energy mgh, which is our gravitational potential energy here. And over here, if we're moving at velocity v, we can say that we have half mv squared plus half I omega squared. Now we can plug in v squared over r squared for omega squared because the object is not slipping. And of course we have beta mr squared for I. And we also have an mgh here because it still has some distance to fall. So all in all, we get mgh minus h equals half mv squared plus half beta mr squared plus v times v squared over r squared, which equals half mv squared times 1 plus beta, because we can cancel the r squareds. Alright, next we need to figure out what v is, which we can do using kinematics over here. We see using x equals x0 plus v0t plus half at squared, we use h equals half gt squared, so we find that t equals square root 2h over g. So it stays in the air for this amount of time, and because we have v equals d over t, we can say that d equals vt, which means that we can use v equals d over t and plug in d divided by square root 2h over g, which equals d root g over 2h. So we have our value of v here, and then we can take our equation up here to solve for beta. So we have mg h minus h equals half mv squared 1 plus beta. We divide both sides by half mv squared, so we get this. Oh wait, we can cancel the m's. So we have half mv squared equals 1 plus beta, which we can then put in beta equals g h minus h over half v squared minus 1. And then we plug in this value of v with this value for v. So we have g times h minus h over 1 half times d squared times g over 2h minus 1, which if we plug into our calculator, we get that all this equals 0.25. So we get that beta is 0.25, and now we know the moment of inertia of this non-uniform cylinder.